Start recording. Okay. So, hi. Good to see you all in person. Although now I don't know who any of you are because I saw your faces last week and now I don't see your faces. So we'll see. But and let's see. So I posted like outline of the notes. And there's just some stuff I want to talk about. I want to finish up logic, a few little last pieces of logic. And I want to start sort of sets and set theory today. And there's actually a group work handout we can start, just because I don't want to spend all semester lecturing at you. Right, that gets tiresome. So any logistical questions before we get started? You guys got the email from Gabriel yesterday. You guys, hopefully, I don't know if it was a little bit late notice, but hopefully people will start going to see him. He's great and very helpful with lots of things, including tech. So I did get some emails about LaTeX issues. I think I tried to respond to them. You can certainly come. I have office hours 2:30 to 4 today. So you can come by if you need to. Okay. And like I said, I think it's due at 11 p.m., but I think I put in like a 48-hour late period, like quote unquote late period, so like you can, if you have issues with the LaTeX or with uploading or whatever, you can have some more time. Okay, cool. So one thing I realized when people were in office hours yesterday is I don't think I ever actually defined the word tautology, and it's on the problem set, which I felt bad about. It is defined in the book, so you can find the definition or you can Google it. It's basically, so let me just like, let me sort of finish up logic. And yeah, tautology. So this is a word, it's a fancy word that's like basically, it kind of means like universally true. Something that's tautology if it's just true no matter sort of what the conditions are. And in terms of logic, in terms of mathematical logic, what I mean is that we build these truth tables and you have some statement that you build up, like you combine statements to build up a truth table. And if you get the last column, if like the statement you're trying to build in the last column, if that's all trues, then it's a tautology. So, and I'll give you some examples in a second, but yeah. So maybe I should say a mathematical statement is a, try to split the board so I don't, is a tautology. I'm going to use IFF a lot for if and only if, like when we define things, it's like if tautology, then this, if this, then tautology, then we call it tautology. If it is true, no matter whether the inputs are true or not, or false. Are true or false. So a very simple example is something like P or not P, right? If something's true, then, if P is true, then not P is false. If P is false, then not P is true. So you could make a simple table of this, just true and false. So that flips the value, right? And then P or not P, since it's or, right, as long as one or the other is true, then it's true. So a lot of times we can sort of state universal logical truths as tautologies, like P or not P being like, yeah, like either P is true or not P is true. So this is a tautology. Okay, does that make sense? Because this column it's all truths. One thing I will say is that like Sometimes like on the problem set, I sort of said, if you're trying to show two things logically equivalent, as long as you get the same column, then you could put an extra column sort of doing the if and only if, and you get all trues, but you don't really have to put that extra column because I think like that first problem I did. So let me just give you two more examples. So another example is something we talked about last time, but we didn't actually sort of prove in the sense of truth tables. The contrapositive, right? So my claim was that P implies Q is the same as not Q implies not P, which you could state something like that. If you wanted to just put this in terms of like purely logical symbols, right? If P is true, then Q is true. Should be the same that if Q is false, then P must have been false, right? That's kind of what we said was the idea of the contrapositive. And so you could build this fairly quickly also. Oh man, this actually has a little more than I thought. Let's see, not P, not Q. P implies Q. Oh. Not Q implies not P. And see, that's where I'm saying there could be an extra column of like, I mean, I guess one thing I could say is like, you don't really need this extra column, but like the book does some things where it just calls this like this statement R and this statement U or something like that. And then this last column could be like R, if and only if U. It'd be like the last column. Like just a shorthand, just because writing all these out gets kind of tedious and long. And so, right, so actually you guys might as well take a minute and start filling this in just to see that it's actually, basically you should get the same truth table for this and for this, for these last two columns. And then therefore, if we did the if and only if thing, it would make a column of all trues. But rather than me, let you guys get ahead of me. I'll take a drink of water, which is not coffee, which is sad. Is this working out? Negate both of these. Also talking to people in office hours yesterday, I noticed like the truth table for implies is still not obvious to lots of people, which it takes time to get used to. That the only way this is false is if you have a truth imply a falsehood. So that's false, but the rest are all trues, which I admit still feels weird, but if this is false. One way I said this in, I think in office hours, not in class, is like, you start from a falsehood, all bets are off. Like if I start from 1 = 0, I can prove the moon is made of cheese or something. Because like you're just out of the realm of like, you're in kind of a realm where anything goes as soon as something's contradictory. Oh wait, I just totally did the wrong thing, didn't I? I was looking at these two columns. Yeah, you guys have to yell at me like immediately. Don't be shy. Sorry, these two columns is the standard truth table for. Yeah, is that better? Okay, and then this one, actually it's not Q implies not P, so I need to go that way. So I think this is is that the only bad one? So that's false. Oh, look. So now, see, you get the same column. And then if you did if and only if the two, you would get true, 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 true. So you don't necessarily have to do the last one if it's an if and only if sort of thing. But yeah. One last one that's sort of fun, or fun, but I don't know, famous and worth mentioning is what is called modus ponens. It's so important that it has its own name, its own fancy Latin name. Modus ponens, which is, it says kind of what we do. It's what you do when you do math or mathematical logic over and over again, which is if we know P implies Q is true, and we know P is true, then what should we be able to conclude? Then Q is true, right? Like, because that's kind of the idea is like, if P is true, P implies Q, so if P is true, then Q is true. So if we know P is true, then that should mean that Q is also true. And so that should imply Q. Right, this is just sort of a foundational law of how we apply logic. Does that make sense? Yeah. So like if P implies Q, and if Q is true, I mean if P is true, then Q is true. Right, that's kind of what that says. And so we can also build this table just to see that it's a tautology. Implies Q. Maybe we'll call this R. So R, that's R. So then we could have R and P. And then if I want to continue to be lazy, I could call this whole thing U or something. So that's U. And then U implies Q. Sorry. So again, take a minute and fill this in and see that it becomes all trues. I didn't pick an example with 3 inputs where I had to do like 8 rows. Okay, so if we AND the first column and the third column, what do we get? Looks like someone tell me what that column should be. TFFF seems right to me. This is only true if both of these are true, right? Then U implies Q. So the fourth column implies a second column. Does that give us all trues? Yeah, because there's never a true implies false, right? So true, true, true. So that's a tautology. Okay, okay. So we get the idea. Yeah. Okay, good. Now I do actually want to go to the screen. I need to. So I wanted to pull up the textbook for a second. The textbook I think is very readable actually, and I recommend that you that you read it. I think I put the textbook. Where did I put the textbook? Here. So I just wanted to, rather than write all this out, I just wanted to show you a page of the textbook and mention it. But yeah, like, even I think like section 1.4 is an interesting section, like just a very readable, like kind of how we think about proofs and stuff. Like I would definitely recommend reading that. And then I think what I wanted was, what page was it? 29. Page 29 of the book. Oh, wait, I need to share screen. Good about that. Okay, so yeah, section 1.4 is good. And then, but if we go to page 29, yeah, this is this logical equivalence. So yeah, some of these things, so for example, I'm actually, one on the homework, you have to prove one of these, demorgans laws, but let me, oh yeah, this list right here. So there's all these different lists. There's all these different like laws. Now, one thing that the book does, which I don't tend to do, is this 3-bar thing, which it's sort of their way of saying if and only if, or that it's sort of a tautology that like P and Q and R and P and Q and R, you know, like that and or are both associative. Remember the caret is and the wedge is or. Things like this, that if P if and only if Q is the same as Q if and only if P. But yeah, at some point they talk about, I'm just writing this, instead of writing, where do they define this? Sorry, I was looking at this earlier. Oh, sometimes S1 is logically equivalent to S2, sometimes abbreviated as. Yeah, I mean, I tend to just use the double-headed arrow, but I think the book's trying to make some claim that there's sort of slightly, maybe not mathematically different, but philosophically different. Like this is just supposed to indicate to you that you're looking at a tautology or something. So a lot of these I think are pretty obvious, you know, like I didn't want to write them all down, right? P and P, names P. I mean, some of them are worth thinking about. P and P or Q is the same as just P. Is that believable? It's basically only true if P is true. There are distributive laws. I think one of those you have to prove on the homework. There's also these what are called demorgans laws, which is the way that sort of like negation distributes over and or. Like if I want to say that not P and Q, how can I make P and Q false? How is P and Q false? If either P is false or Q is false, and that's kind of the right-hand side of that equation, right? Like if not P is true or not Q is true, then right. So we'll use some of that. Okay, so I just wanted to show you this table because I don't want to write all these out. So page 29, if you want to look at these. Okay, any questions about any of these? What are, like, what does that mean? Yeah. Oh, like, yeah, I don't know how that would translate back to like something with like plus and times, you mean something like that? Or just like, that's a good question. I mean, in terms of these logical statements, does it make sense so that like basically if you have P and P or Q, the P or Q is kind of redundant? Yeah. Right. Okay, but you're trying to like connect it back to, yeah, I mean, there are examples, there are other examples, I think maybe like max and min or something like that. Like if you had the max of it's interesting. So like, yeah, trying to find operations that like fit some of these things, like if you had the max, if you had two numbers A and B, and you took the max of A and then the min of A or B. Is that A? I'm just trying to think of this on the fly, so I could be wrong. If A is bigger than B, then this would be B, and the max of A and B would be A. If A is less than B, then this would be A, and then the max of A and A would be A. So that's interesting. Yeah, there are some mathematical. It's kind of fun to think about like equations like that and try to think like what different kinds of operations would make it true, you know? So no, that's an interesting question. I'm kind of amazed I came up with an answer off the top of my head. Okay. But I think that this equals A. So that could be considered an absorption law that way. But yeah, interesting. And then idempotency is kind of weird, like when something like that actually comes up in linear algebra. Sometimes when you have a matrix that squares to equal itself, like projection matrices, like if you, I don't know if you don't necessarily have to take linear algebra to take this class, but like if you project from like 3D down onto some 2D subspace and there's like a matrix for that, then if you do it again, you still just get that same 2D subspace. So like, so yeah, here, I don't know, it's kind of fun to, actually I should stop the share because posterity's sake. So, don't want myself on screen. Okay, so this could be an absorption example. An idempotent is anything that squares to equal itself. And it just comes up more in abstract algebra. But for example, if we had the matrix, like a simple example would be this matrix is like projection onto the XY plane. If you haven't taken linear algebra, don't worry about this. It's not a big deal. But that's projection on the XY plane, right? But if you square this matrix, you get itself. It's P, and you could check. I mean, it's sort of obvious too, because if you project on the XY plane and then take this and project on the XY plane, you're at the same point. So there's different, yeah, so these words that start showing up in math are kind of interesting. Like idempotent is a word that starts to show up in other places. So cool, oh good. I like that, those kind of questions. All right. Okay, so I think that's all I wanted to say about logic. Any questions? Anything lingering? I mean, you can also, if you do read the book and come in and say like, this thing was in the book and it confused me or something, then it's absolutely a valid thing to bring into class. We're office hours. Otherwise, I think we don't need the screen again for a little while. Okay. So let's jump into sets. We'll talk about sets for a little while, just kind of introduce them. And then I have this sort of handout, just kind of like just playing around with sets and getting used to them. So we can do some group work. So like I said, you're not just sitting and watching me. 85 minutes can get kind of long. Plus, I have another 85-minute class right after this class. It's like I want to give myself a break a little bit. Ooh, maybe if I put you in group work, I'll have time to go out and get my coffee. That's exciting. Okay. Sets. So I think I might have even said this like last Tuesday, that you can put almost all of mathematics in the language of sets and maps between sets. That's sort of an interesting like modern perspective of what math is. And so we need to like thinking fundamentally about what is a set, and it's not anything that complicated. It's just a set is just a collection of, as a collection really, could be sort of anything of elements, just whatever belongs to that set. So just like, I don't know, examples I wrote for myself, like that's a set, just the numbers 1, 3, 5, 7, and 9. But you know, it can be more abstract. I think you'd have a set that's the Eiffel Tower, the Statue of Liberty. What's another good sort of like, somehow I ended up on the Wikipedia page over the weekend for like the largest statues in the world. There's some insane ones. There's some ones like in like Buddha statues, and there's some like important Indian guy, like founder of India, who's like, there's a statue, it's like, they show the people next to it, it's like 1,000 feet tall, you know, it's like these crazy statues. A friend of mine went to North Korea, they have like crazy statues, like the deer leader, you know. What else do you want to throw in this set? Motherland Calls of Russia. No, that's good. What's it called though? Motherland Calls. Cool. Oh, did you? Yeah. It's sort of interesting to sort of like, so easy to go down Wikipedia rabbit holes, right? Or YouTube rabbit holes or whatever. Okay, or you know, but you can give you know, one thing we're going to talk about is giving sort of conditionals. So like the set of all cars built between 1983 and 2004, I don't know, right? Like you could sort of say something like that. You know, so there's like different ways you can write down sets. Then there's just like a lot of property, like a lot of ways we talk about sets, like they're unordered. So I'm just gonna sort of say a bunch of things about sets and then we can just start playing around with them. So it doesn't really matter, like the set 1, 2, 3 is the same thing as the set 1, 3, 2. So that's important, like as a distinction between sequences or something like that. And we'll talk about ordered pairs, like, you know, like if you want to define like an ordered pair of elements like in the plane or something, it matters what's first and what's second. And actually there's a way to define that in terms of sets, which we'll talk about, which is kind of cool, but they're considered just, it doesn't really matter how you list them, what order you list them in. You could list repeats if you want, like that's kind of a goofy thing, but I mean, it's just sometimes you're looking at some set where you're not really sure what all the elements are and you start listing things, and but they're kind of described abstractly, and then you realize, oh, actually the first thing and the fourth thing are actually the same thing. So that's, you know, so we can have repetitions. It doesn't really change what the set is. So these are examples. So for example, the set 1, 2, 3, 2, 1 is really just the set 1, 2, 3. So I'm not saying, I mean, I guess what I'm saying is like, if I call something 1, it's the same 1 over here. I'd have to like somehow distinguish that it was a different one. Like I could have like 1 prime or something if I wanted to, and that would be like a different copy of 1 or something. And then that would be a different set. But if we're just talking about sets of numbers, then we could do that. Oh, so there's the notation, which I think I might have mentioned already. Oh yeah, I think I mentioned already in terms of like when we started doing proofs of like axiomatic proofs that like element of, you know, we say, we write that little epsilon looking thing. So we say A is an element of S, and write this sort of like, I put fancy serifs on there. And write A and S if A lives inside S, if A belongs to S. Belongs to S. We tend to write lowercase letters for elements and uppercase letters for sets. But then we'll also have sets of sets. And so that's a little bit of a weird, so like that doesn't always work. Let's see. Oh, one of the big things we're going to do, kind of like this one, is we're going to often define a set by a condition instead of like writing out all the elements. Like, so sets are often, usually maybe, often given by conditions. For example, we could write the set like the x's in the integers such that, so, okay, so you read this, sorry, I'm so ingrained in this that I just did that automatically. We say, we read this as such that, or like this is the condition, such that x is odd and 0 is less than x is less than 10. Right, we could define a set this way, something like this, where we just sort of say, you sort of say where it lives. It's like, you kind of want to specify first, like, you know, where you live. I guess I'll say some books actually do write things a little bit differently. Like they'll write just x such that x is in Z and x is odd and x is between 0 and 10. Right, you could write that. But most mathematicians, I think, tend to write this, where it's like, the first thing you kind of want to specify is where it lives. Like we're talking about integers. And then we say what the condition is on the integers. So these are the same. But I tend to sort of prefer, I don't know, whenever I see this, I'm sort of like, before I even get to the vertical bar, I'm like, wait, where does it live? Maybe it's just an aesthetic sense thing or something, but I like it to be told where it lives immediately and then say what the condition is. So it's kind of just maybe a silly point, but this is a set we've already seen on the board, right? What is this set? Yeah, that one, right? Okay, not too tough. So you could say, you know, you could define a set just by listing its elements, or you could define it by some conditions. And often if it's an infinite set, or if we don't really know what exactly is in this set, that's how we'll sort of describe sets, and then maybe try to figure out what the actual elements are. Okay, does that make sense? Yeah, okay, so, we also have subsets. Subsets are important. I almost just have to give you a bunch of little concepts, then we can start to play with them. So, sets have subsets, right? So we can take subcollections. So for example, you know, 1, 5, 9 is a subset of 1, 3, 5, 7, 9. And the notation that we tend to use for this I guess one thing I should maybe say that I didn't say that explicitly is that like we use these sort of like curly braces for the set notation. We put commas between elements, but I guess that is kind of, some stuff is so obvious that I need to say it. But the notation we use for this is this. So it's this thing right here. Now it's a little weird. I think it's supposed to be reminiscent of like less than or equal to. Because a set can be a subset of itself, like we consider a set a subset of itself. There is a symbol without this that's like a strict subset. So, or what's called a proper subset. So like we can write, you know, for any subset including T, for any subset, any subset S of T, including T itself. That's kind of why this little almost like equals part of the sign there, including T itself. Just saying that T is a subset of T is always true. And there is sort of like proper, there's a notion of what's called a proper or strict subset. So like S is a subset of T, but S is not equal to T. And sometimes there is a notation for this, which is like S, just without the like, it's like strictly less than instead of like less than or equal to. But I think, especially when you're doing anything abstractly, we tend to like to use this symbol more just because you do want to include the case of the whole set. Makes sense what I'm saying. Again, lots of things are just decided, like this is the convention, you know. But okay, so we can have subsets. We can do weird things like have sets of sets. Like for example, we could have the set and in fact, we'll see this later in the semester in some natural ways. So for example, we could have the set, which is the set, it contains the set containing 1, the set containing 1 and 2, and the set containing 1, 2, and 3. It's kind of a goofy thing to do, but there are reasons why we might want to do this. And now you have to think about things kind of strangely like let me put two things on the board and you tell me what's true, which one's true. It's also disturbing that these symbols are really close. If you don't write carefully, you can really mistake one for another. Which one is true, the first one or the second one? Is the set 1, 2 a subset of S, or is it an element of S? It's an element, right? So this one's actually true. This one's false, because it's not a subset. We could say the set containing just the set 1, 2 is a subset of the whole thing, because yeah, in fact, even up here when I wrote A is not one of S, let me just pull this down for a second. You could write, once we know the subset notation, you could write A, just the set containing just A is a subset of S, right? So it's kind of what I'm doing here. So this is actually okay also. Yeah, question.
So are sets, does the set have to contain one type of, can you have sets in the set?
Yeah, like, could I have like the combined of the first 2 sets up there? You can, yeah, because it's supposed to be just no restrictions whatsoever. So I could have the set that contains 1 through 5, 7, 9 in the Eiffel Tower. Of course, that's kind of weird, right? Like, yeah. Yes. The set. Right. Yeah, like that's right. I can say other things that aren't true. Good. So like, is 1 an element of S? And the answer would be no. Because it's like, it's a set just containing these collections. It's kind of weird because it does feel like if something lives inside something which lives inside something, then it should live inside the thing. Sorry, that was the most horrible way I could have said that. But like, yeah, it's like, if you think about like, this is like, you have these 3 boxes that live inside S, right? Like, it's like a big box, a big chest, and it's got 3 boxes inside it. And this box, the first box contains just the number 1, the second box contains numbers 1 and 2, and the third box contains numbers 1, 2, and 3. And it's tempting to say that like 1 lives inside the big chest, which it sort of does. Maybe that's why maybe it's not the best metaphor, because mathematically we would say no, this is not an element of the set. This set has exactly 3 elements. Yeah, S has 3 elements. And the number 1 is not one of those elements, right? The set containing the number 1 is one of those elements. I mean, some of this is goofy and it's just worth kind of doing just to be used to it. But there are cases later where we build certain sets by like sets of sets. Like if we wanted to build them rigorously, like things like you've heard about mod using modular arithmetic and stuff, like when you want to do mod 10, which is basically taking the last digit of a number. Like you can sort of rigorously build that as a set of subsets of the integers, or like, we'll see later that the rationals you can define rigorously as sets of sets. Like if I want to have like, what does 1/2 mean? What I really want it to mean is somehow the pair 1, 2, but I also want it to mean the pair 2, 4, or the pair 3, 6, or the pair 4, 8, or the pair 5, 10, or the pair -1, -2. And so like, there's a sense there in which like each rational number could be thought of as a set itself, like all the things that's equivalent to. We'll do all this later. I'm just like trying to give you senses of like why we might actually care about this mathematically. Okay, and then okay, so then the next really weird thing is the empty set. We got to talk about the empty set. Empty set is a strange animal. So the empty set is the set with no elements. But it comes up a lot in math, and it's a useful conceit. So or wait, did I talk about? Okay, well, I'll do that next. So the empty set. So this is usually written just as like a 0 with a slash through it. And it's the set containing no elements. Set with no elements. By the way, in LaTeX, there is a / empty set, but it really is just like a 0 with a slash through it, which I don't like. So the actual LaTeX command I like for this is /var nothing, VAR nothing. I should, the handouts, I'll post a text source for the handouts also, so you can look at those. So the handout will have the empty set on it, so you can look and see. Set with no elements. So what does that mean? I mean, there's a lot of things we could say about the empty set, and I don't want to spend all day on it today. We'll probably come back to it, talk about it more. But I just want to say that just so that that's out there, there is a set we consider a set with no elements. So one definition could be or not a definition, but more like a statement, a true statement. I'll just say we can say like say we're in the integers, for example, or just any set, in any set, X is not in the empty set. So this is a true statement, like X is never, any X you actually have is not in the empty set. Kind of a strange thing to say, but the empty set itself is a subset of every set. But for any set S, the empty set is a subset of S. That is true. Because if I have this set of just the numbers 1, 2, and 3, there is sort of a subset of that, which is nothing of the set. Like none of it is considered a subset. I mean, you may not also consider that a proper subset. There's these sort of extremes. So just as an example, if S is the set 1, 2, 3, then the subsets, what are all the subsets of S? Well, we could have just the set containing 1, just the set containing 2, just the set containing 3, a set containing 2 of these things, the sets, each of the possible sets containing 2 of these things. And then we also have the whole set itself. And we have the empty set. So like the subsets of S are kind of these 8 things, or you sort of see that like there's 3 possible sets with just 1 element, there's 3 possible sets with 2 elements. There's 1 set with all 3, and there's 1 set with nothing. Okay. Yeah. Yeah, again, I'll talk about the empty set more later because I think it's kind of there's lots of weird things you can start to say, like if I say for all X in the empty set, X is red, I claim that's a true statement. Maybe I'll go ahead and say this just because it's so funky and we want to get used to it. So I guess what I want to say is all statements about elements of the empty set are true. And if you think about it, it has to do with the truth table for implies. So all statements about elements of the empty set are true. So, for example, if X is in the empty set, then X is red. When is the implication false? When it's not right? When it's not right. Oh no, when is the general implication false? Like when are they, how do we falsify the implies? I mean, yeah, sort of like, but yeah, yeah, like the only time this is false is if this is true and this is false. What's the problem with that? This is never true. So we're always in that false part of the P implies Q truth table. It's weird. So like, right, this is always false. And so this is either F false implies false or false implies true, both of which are true. I always debate whether to tell the story, but I got myself in trouble once using this. This is sometimes called vacuous truth. should I tell the story? I was in college, like you guys. I was having brunch with two of my friends. One friend liked to hook up with people. She was very into hooking up. The other friend had like never touched a person ever. So the first friend is telling us the story. It's like a Sunday morning. So she's like, oh, like I hooked up someone, okay. So she's like, oh, I email this friend of mine from high school every time I hook up with someone. And she was like, and I looked at how many emails there were, and she was like, oh my God, it's bad. And I was like, oh. I turned to the other friend and I said, you do the same thing. And she's like, what do you mean? I was like, every time you hook up with someone, you email her friend. She was like, what are you talking about? And I was like, it's vacuously true, right? Because you've never hooked up with anyone. So, and they both basically got really mad at me and like, we're like, what's wrong with you? And I thought I was being funny, like using my nerd skills to be like, that's a true statement. So, I don't know if I should have told that story, but okay. But it's a nice illustration of vacuous truth, right? Okay. Exactly. Math is applicable. So, I mean, it's a good illustration of it, but this is why I tell that story, but it does not reflect well on me probably. Okay. So, anyways, yeah, so that's called vacuous truth. Okay. So we'll come back to, again, there's a lot more weirdness with the empty set. The other thing, oh, so I've already actually put this on the board. You can look at the set of all subsets of a set, and that has a name, because we could take the set of, I could make this a set actually. Like the set of all subsets of a set is called, it's called the power set. It's just a name. You can sort of see why. I mean, if I have a set with 3 elements, how many subsets were there? How many total are there? Total? All the subsets. Like I had 3 elements. How many subsets did I end up with? How many things are in that boxed area? 8, right? I feel like I said something confusing because people were saying 3, but there's 8. There's 8 things in there, or I heard 3. Anyways, there's 8 things in there, right? And there's an argument. How is 8 related to 3? So many different ways that you could relate 8 to 3. 2 cubed. It's 2 cubed. You could sort of, there's arguments which we could talk about that, like if you have a set with like 10 elements, it has 2 to the 10th subsets. And there's nice arguments for that. But that only works if you include the empty set actually in your list. So, question or no? Sorry. Okay, so yeah, so let me just write that down. So a set, given a set S, the set of subsets is called the power set of S. So set S, the set of subsets of S is called the power set of S and is denoted P of S. So maybe it's just a smaller example, like if S is the set 5 and 11, then right, there's the empty set, there's a set containing 5, there's a set containing 11, and then there's the whole thing. Does that make sense? Or the example above is for a set of 3 things. We are eventually going to be looking at infinite sets and the power sets of infinite sets, and things can get complicated, but okay. And then the other, maybe the last thing, sorry, I know I've been talking for a while, is what's the last thing? Yeah, okay. So making new subsets from old subsets. So like or making new sets from old. Something like how we made new logical propositions by using and or and implies and stuff. We can do something similar here. We can do unions, intersections, and complements. I'll explain what all those mean. I mean, you can guess what union and intersection means. So A union B, written with this little U symbol, is the set of things that are in A. It's the collection of all things that are in either A or in B, right? In A or in B. Intersection is in both A and B, right? So in A and in B. So yeah, union is really connected to logical or, and intersection is connected to logical and. So just as examples, like if A is 1, 3, 5, and B is 3, 7, 9, right? Then what's A union B? Right. A union B is just, so there's an overlap, so it's not double counted or anything, but, and what's the intersection? Yeah, it's just 3 is the only thing that's common to both, right? And so we write this little cap for, in fact, sometimes I should just write like the LaTeX. I think the LaTeX for this is cup, and the LaTeX for this is cap. Okay. There's also complements, which is like, if I'm in a set, everything that's not in that, like if I'm in a larger set and I take a subset, the complement is everything not in that subset. So let me just do it over here. So complements. So for example, if we have the integers and we have S is the odd integers, right, then the complement is the even integers, things that are not odd. So S prime, it's often written, is, we could also write it like this, Z minus S, which is everything in Z minus everything, you take away everything in S. These are both notations. This is the even integers. Right, so these are both, there's also, I guess there's also like set subtraction, which is like things in Z, but not S. Okay, those are just notations. And again, we'll dive more into some of this stuff as we go. Let me share screen again and actually pull up this handout. Sorry, I have to give us more than like 18 minutes to work on this, but we can also start Thursday and keep going with group work. So this is actually on the class meeting page at the bottom. So Right, so some of this is just like list the elements, then it's going to go backwards, give a conditional, like we sort of said here for like what's the condition to be along to one of these sets. And then there's some like true, false. Venn diagrams, I don't have to define that, right? You know what a Venn diagram is, where you just draw circles representing sets. And the intersection is the intersection, and the union is the union. So, yeah. Let's, so you guys are gonna take like the last 15 minutes and just get started on this, and then we can keep going with it on Thursday? Sound like a plan? How are we gonna break into groups? I just break you guys up. I like to go to the boards. That's one reason I like these classrooms, is there's lots of boards. So there's about 15 of you, so maybe about 3 people per. So do you 3 want to go to that board? You 3 maybe go over there. What did I do? Wait, no, then you, and you in the back. You guys can come up and use one of the front boards. And then, sorry, I'm just kind of randomly doing this. You 3, maybe back there, and then you 3 over here. You can try my fancy chalk if you want. You should try the bad chalk and then the fancy chalk. So you can erase. Let's get going. By the way, introduce yourselves to the people in your group. Say hi. Say who you are, what year you are, whatever. Hello. That's the fancy chalk. So you can also pull this up on a device. It's on that class meeting page if you can't see it, but. Excuse me. Oh, by the way, the capital N, sorry, I didn't say that. It's the positive integers. It's called the natural numbers. I just realized I never told you guys. N is the positive integers. Yeah, so write your answers on the board so you can like look at what other people are doing. Is 1 prime? It is not considered prime. 1 is not considered prime. Like we talk about that later. Oh, let me pause the recording also, sorry.